So redox reactions are actually not anything new in terms of the types of reactions that you've seen. It simply is a different way of looking at reactions that we've already seen. So we're looking at it from a different perspective when we talk about redox reactions. And in fact, the redox reactions are definitely familiar to you guys. And let me make sure that I first clue you into the fact that redox is a combination of two separate terms, reduction reactions and oxidation reactions. So examples of redox reactions include how batteries work, but also something like how wood burns in a fireplace, the idea of rusting, and even something as strangely non-chemistry related as ripening of fruit. So let's take a look at some specific examples and show you the reactions. So here's an example of a redox reaction. And the one thing that you might note here, and you might think is the only reason why we call these redox when you think about oxidation, is that it includes oxygen. Now that's only one way in which we define something as being a redox reaction. In this case, we've seen this reaction before. This is the combustion of methane. So we might call this a combustion reaction or a direct combination reaction. But today we're going to start calling these things redox reactions. I'll get into the definition soon enough. And here's yet another one. This is the rusting I was referring to earlier. And again, this looks like a fairly familiar thing. Probably something that you saw in the fall term, either with me or with Oxborough. And it also is a combustion reaction, but it's a very slow combustion in terms of how it happens in time. But again, we have the same thing. It seems like oxygen is involved, but perhaps, in fact, I shouldn't have even given one with oxygen, so you can see that oxygen does not necessarily need to be involved in a redox reaction. So what are the ways in which we define something as being a redox reaction? Let's take a look at that. All right, so the first thing is that oxygen is going to be involved. And in this case, there are two ways in which oxygen can be involved. Either we have that oxygen's a reactant, and if that's the case, we call it an oxidation reaction, or oxygen's a product, in which case we call it a reduction reaction. Okay, so when oxygen is involved, it's a redox reaction for sure. All right, this one's a little weird because it's not something you've necessarily looked at before, but it was happening in almost all the reactions that we dealt with. And that is that electrons from one compound or element are transferred to another compound or element. And let's show that with this reaction. Now I want you to notice with this reaction, there's a couple of strange things that we've not included in here. One of which is that see here we have the silver as an ion. It's not there as an ionic compound. So the spectator ion that is associated with the silver is not shown in this reaction, but it might be something like a nitrate ion that we haven't put in here. So we've excluded it since it's not going to be really important to us. But what I want you to see here is that in order for us to have elemental silver form, it needs to be able to take up a couple of electrons. So indeed, I need to show the movement of the electrons. In this case, it would have to be 2 electrons that would be transferred from the copper to the silver. Now, what am I saying? It's not 2. Jeez. From the copper to the silver so that you can make the solid silver. Now, in the end, it is true that 2 electrons are released, but I haven't balanced this whole reaction, so don't worry too much about how many are moved. Now, in this case, in terms of this concept of oxidation versus reduction, the copper is the thing that's being oxidized. Copper is being oxidized. So when you lose an electron, you are being oxidized. So in this case, clearly the copper is what's being oxidized in this reaction. On the flip side, the Ag plus, the silver ion, is being reduced because it is gaining an electron. All right, so you can see there that the thing that is gaining the electron has to be the silver ion. And in fact, there's a kind of a nice way to remember this, which is through the phrase oil rig. Okay. And this means oxidation is loss of an electron, reduction is gain of an electron. So if you remember oil rig, you can never fail to understand those two concepts when it comes to oxidation reduction reactions. Another potentially obvious thing to understand here is that if something is being oxidized in a reaction, then another thing must be being reduced at some point in that reaction, because you have to get the electron from something, right? So if one thing is being oxidized, then something else must be being reduced. In fact, it's sometimes easier to see how this is happening by looking at what's called half reactions. So if we're going to look at this whole reaction right here that I'm pointing out, let's change this and make it into what are called half reactions. It's kind of a weird thing to do, but in the end it makes it a lot easier to understand what we're going for. So here are the two half reactions that make up that whole reaction. And what you can see here is now I've suddenly included electrons as a product of this reaction here, this half reaction, where copper solid is oxidized, it becomes oxidized to form copper ions and 2 electrons, free electrons that are floating around out there ready to combine with something else. And then similarly, let's do it with the silver. All right, and in this case you can see that the silver has picked up an electron, so it's gaining an electron. Don't forget the oil rig thing though, so rig is reduction is gaining, so this is a reduction reaction. And again, this goes back to the original reaction that we had right here. I just broke it up into two so that you can so more clearly see the actual oxidation and reduction going on with the two elements that are involved, or element and ion. All right, so there's one more way in which we can define an oxidation or a reduction reaction, and I've run out of room here, so let me just, this is going to be number 3. And I'm going to use blue in order to explain number 3 here. I'll just squeeze it into here. Okay, and that is that we look at it from the perspective of the oxidation number. Okay, so this is a new concept, the oxidation number. So in the first case, if a compound or an element or an ion decreases its oxidation number, and again you haven't learned what an oxidation number is quite yet, but you will in a second, in a reaction, then it is reduced. Alright, so let's take a look at what do I mean by that. So let's go ahead and look again at what we saw with those half reactions I had above, right here. Okay, and we're going to focus in on, in this case, let's go for the silver. So the silver has an oxidation number of +1. So you can see that the oxidation number is the number that associated with the charge of the element or the ion. So in this case it's +1. And in the reaction it becomes, as you can see here, Ag solid. Okay, we can go back to here and see that it goes from Ag plus to Ag solid in the full reaction. We can see that occurring in our half reaction as well. So let's just focus in on what has just happened there. If we know that it's going to become the Ag solid, it's very important that you have the states of matter here. And Ag solid has an oxidation number of 0. Anything in its elemental state is going to have an oxidation number of 0 because it's uncharged. All right. So in that case, you can see how the oxidation number has decreased from +1 to 0, and therefore the element, compound, or ion has been reduced. Similarly, we can flip it around and figure out how something has been oxidized. Alright, so all I did was copy and paste it, and notably I changed this from decrease to increases and from reduced to oxidized, but it's the same concept. If a compound, element, or ion increases its oxidation number in a reaction, it is oxidized. So let's take a look at how the copper performs and confirm how this is an oxidation part of the reaction. Okay, and once again we can see here that we have an oxidation number of 0 because it's copper in its elemental state. And when the reaction is over, the copper has an oxidation number of +2 or 2+, so therefore it has increased, and we refer to this as being oxidized. The copper has been oxidized. So now we need to take a look and see how it is that we assign oxidation numbers. And there are a whole bunch of rules associated with this that you're going to need to follow for the in-class assignment I'm going to have you do right after you view this. Okay, the first rule is that the oxidation number for an atom in its elementary state is 0. And of course, we confirmed this moments ago because we saw that copper solid is going to have a 0, and silver in its solid form is also going to have a 0 there. All right, so the next rule is that the oxidation number for groups 1 and 2 ions is the ion's charge. So this is the alkali metals and the alkaline earth metals. Actually, I want to make sure that I add common charge because we can always strip more electrons away to make something an uncommon charge, but in its most natural ion form. All right, that being the case, we all know that the alkali metals, the group 1 metals, are always going to have a common charge of +1, whereas the alkaline earth metals will have a +2 charge. So, for example, something like sodium, or in this case, something like maybe magnesium. Okay, let me scooch this up for rule number 3. Rule 3 is that oxygen usually is a -2. In other words, its ox number is a -2. However, in peroxides, it is a -1. More on that later, but just note what I write. All right, so let me scooch this up so I can get to rule number 4. Actually, you know what? I need to run out and turn off the sprinkler. Hold on. Looks so bright and green now. All right, number 4 is that hydrogen is a +1 oxidation number usually. There always are exceptions, unfortunately. So just write down what I write here. All right, and the fifth and final rule that we have here is that all other oxidation numbers are determined by the zero-sum method, sometimes called the net charge sum method in the case of polyatomic ions. Okay, so I guess I'll give you a couple of examples and then I'll let you have at it on the worksheet that I'm going to give you right now too. All right, for this first one, we know that Mg is an alkaline earth metal, so that's going to have a +2. And we know ultimately that this thing has to have a sum of 0. So if we know that we have a +2 for my Mg, and we have the Br, but it has a subscript of 2, that means we have to make sure you understand you're going to multiply whatever Br's oxidation number is, which in this case I'm just going to say is X, by that 2, and that must equal the charge of the entire compound, which is a 0. So the only number that would satisfy this is if the X equals a -1. So in this case, if Mg is a +2 from the rules, to determine the charge of the oxidation number of our Br, it is a -1. Ridiculously easy, right? Let's do the same thing with this SO3 2- polyatomic ion. We know that oxygen is going to have a -2 charge. All right, again, given to us by those rules. And we're going to say that in this case, we're going to make X is our oxidation number for the sulfur. And we know that we have 3 oxygens, so I'm going to have a multiplier of 3 times my -2. And that, again, has to equal my net charge sum, which is a -2 charge. Okay, so the only thing that could satisfy this, given that this is a -6, this is a -2, then clearly the X has to be a +4 in order for us to be able to solve that equation. So we have oxygen as -2, sulfur as a +4. All right, I'm going to see if you guys can figure out this one all on your lonesome. All right, and then just if you think you know the answer, come up to me and show me. Bye.